Well, hello class, and thank you for watching. This is going to be our first review for our second chapter, which is power, polynomials, and rational functions. In this review, we're reviewing sections 1.1, 2.1, 2.2, and 2.3. Let's begin by going over how to graph quadratic functions in their standard form. So here we'll use the vertex, which would be +3, -9, and plot our first point there on our graph. So +3, -9 would be there. And in order to plot the second point, we're going to simply just identify the y-intercept. So we're going to evaluate our function when x is equal to 0. So 2 times 0 minus 3 squared minus 9. And let's break down let's do this with our 84. We'll type in 2 parentheses 0 minus 3 squared minus 9, and we get a value of 9. So our y-intercept is 9. Now, because our quadratic, again, is symmetrical, is symmetrical through this vertex, through the axis of symmetry, and we have a point, this point here, that is 1, 2, 3 units to the left of this axis of symmetry, then that means that there has to be a point 1, 2, 3 units to the right of this axis of symmetry. So that will connect, again, those points, and our parabola will look something like this. Let's look at example number 2 now. So for example number 2, we want to identify the vertex first, which is at -1, -3. So that's there. Our y-intercept would be -3 times 0 plus 1 squared minus 3, which is equal to -6. And again, so that's that point there. And our axis of symmetry is this vertical line there. And because of the symmetry, since this point is only 1 unit away from this axis, that means that on the opposite side, there has to be another point that's also going to be 1 unit away from that axis. So plotting and connecting those 2 points with a parabola, those 3 points, with a parabola, gives us a graph of our quadratic. Now let's look at example number 4. So here our vertex is at +2, +7. And let's identify our axis of symmetry. Let's see. Our axis of symmetry, we know it's going to be this line right there. But let's identify our y-intercept. That equals to -9. So 0, -9 would be down there. And again, because of the symmetry, since this point is 2 units, count them 1, 2, 2 units away, 1, 2, 2 units away again from these axes of symmetry, that means that on the other side of the axis of symmetry, 2 units to the right of this axis, has to be another point. So we're going to graph our parabola again like this. Now for the fourth example, our vertex is at +1, 3. Sorry, I need this. There we go. +1, 3. There we go. There's our axis of symmetry. Our vertex, which our axis of symmetry is going to be this. Let's now find the y-intercept. Let me start over, sorry. So 0 minus 1 squared, that's going to become 5, and then plus 3 is 8. And again, because of the symmetry of the parabola, we know that we're going to have a point here as well. So this is going to be our quadratic, the graph of our quadratic. Now, for the next questions, we're asked to use the quadratic function to determine the vertex of the parabola. So here we're going to find that again by identifying again the maximum and with the location of the maximum value or the minimum value here. So we'll start by first using the formula of negative b divided by 2a, which is negative of negative 8 divided by 2 times 1, and that equals to a value of positive 4. We can again check this with our Inspire. And we end up with 4, so x is equal to 4 like I said. And then plugging in that value of 4, we're now going to get the y coordinate of the vertex. So 4 squared minus 8 times 4 minus 10. And that's equal to negative 20, 26. So our vertex is at positive 4, negative 26. Now let's do the exact same thing with example number 6. So negative alpha y equals to get the fraction, and we're going to write a positive 24 on the top and 2 times 4 in the bottom, and that equals to negative 3. Let's plug that value into our function. So we have 4 times negative 3 squared plus 24 times negative 3, and then minus 15. So our vertex is at negative 3, negative 51. Now our next example. Now remember, when you write this into Edge Elastic, make sure that you put the parentheses around this. Again, write this as an ordered pair as a coordinate point. I want the vertex again represented as a coordinate point. So write it again in the parentheses as a coordinate point. So now our next example. All right, so we have negative. Let's put in the fraction, and we're going to type in negative 18. That's our b. And 2 gets multiplied with the value of a, which is negative 3. And we end up with negative 3. And now let's plug that in. So we have negative 3 x, which is negative 3 squared, minus 18 times that negative 3 plus 9. That equals a total of 36. So that's your vertex. And finally, the last, or the 8th example here, the last one of these. Oops, I forgot to put the negative sign in the front. We have a positive 30 divided by 2 times negative 3, which is, oh no, negative 5. So let me try that again. Why am I putting 20? Sorry about that, guys. Oh, we'll get it right eventually. 30, there we go. So we get 3. So our x value is 3. Now let's plug that in to figure out the y value. I don't know why I'm writing it down, could just write it into our calculator here. So -5 parentheses 3 squared plus 30 times 3 minus 45. That equals to 0. So there you have it. Okay, let's now move on to the next example, to the next page. So on the next page, let me move this out of the way. We're asked to figure out, again, determine the maximum height that the football will reach and the time in which it reaches its maximum height. So let's see what that is. Okay, so the height of a football that is kicked into the air is modeled by this equation. So we want to determine the maximum height. Well, we first have to figure out the time, which is t, that is going to reach its maximum height by using the same formula as in examples 5, 6, 7, and 8. So negative b divided by 2a, where here the a would be -16 and b would be 96. So let's not make a mistake here. And 2 times -16 equals 3. So there. Now to figure out what the actual height is, we're now going to plug that 3. We're going to plug in that 3 into the function. So we're going to evaluate the function h of t when the time is 3. So -16 times 3 squared plus 96 times 3. And that equals to 144 feet. Therefore, the maximum height of this football is 144 feet after, which is reached after 3 seconds. Now, number 10 does something similar, but this one is asking us to determine what the minimum cost, how many computers must be made daily to minimize the cost, and what is that minimum cost. So here, we'll start by first determining, again, the number of computers that have to be made on a daily basis. So x is equal to, on your assignment, double check again that this is a minus and not a plus. I think there might have been a mistake, and there was a plus sign instead of a minus sign symbol there. So our b here would be a -120 and 2 times +3. Which is equal to 20. Now let's plug that in. Let's plug that 20 into the function now. So let's evaluate the function when x is 20, and let's determine what the minimum cost will equal to. And plus 2,000. So that's the minimum cost. So to answer this question, how many computers do they have to make daily? They have to make 20 computers. Computers must be made daily to minimize the cost to $800 per day. So they have to make 20 computers in a day to minimize this cost to manufacture these computers, so $8 a day. Okay, now let's look at leading terms. And let's now look at section 2.3. Using the leading term, we're going to determine the end behavior of this polynomial function. So looking at the leading term, this one right here, because of the odd exponent, the odd degree, and the negative coefficient, this polynomial is going to have the exact same end behaviors as this power function here. So the end behaviors of f of x will be that as x approaches negative infinity, the function increases without bound. So that's approaching positive infinity. And on the right side, as x increases, the function decreases without bound. So this is the descriptions of the end behavior to this polynomial. Now for the next polynomial, since the leading coefficient again is an odd degree, an even degree 6, an even degree, and a positive coefficient, then this polynomial is going to have the exact same end behaviors as this power function here. So as x decreases, the function values increase without bound. And as x increases, the function values increase without bound. Okay, now moving on to example 13. Due to the leading coefficient, this polynomial is going to behave like the following power function, like this power function, because of the odd exponent, the odd degree, and the positive coefficient. So here, this is, so that means that as x decreases, the function values decrease, and as x increases, the function values increase. And the last one, well, the last one is like number 12. The only difference is that it's upside down. So the even exponent and the negative coefficient of that leading term makes the will make this polynomial behave like this power function. I'm sorry, the ends will behave like that power function. So here, as x decreases, the function values of this polynomial are also going to decrease, and as x increases, the function values will decrease, just like this power function here. Now, working backwards now, we can determine again to describe the power and the coefficient of this polynomial, of these three polynomials, using the leading coefficient test. So if all of these are polynomials, I know I can write my polynomials in this format. And what I want to do again is determine what is this number in the front. Is this number going to be positive or negative? And what type of degree is this polynomial going to have? So here, the leading coefficient on this one is behaving exactly like this power function, because this end is down and this end is up. So it's behaving exactly, like I said, like this power function right here. Well, this power function occurs when this exponent n, the degree, is an odd number. So our degree has to be some odd number, and because of the number of turning points, 1, 2, 3, 4 turning points, it has to be an odd number that's going to be greater than or equal to 5. Now, because again, it's behaving exactly like this power function, we also know then that the exponent, the leading coefficient, the number a, the leading coefficient, not the exponent, but a, the leading coefficient, has to be a positive number as a result. Now for number 16, this polynomial, again, since the end behavior of this polynomials are, again, both increasing without bound, that means that it's behaving exactly like this power function here. And these power functions occur when the exponent is an even number and the leading coefficient is positive. So our leading coefficient is equal to a positive number, and the degree is an even number that will be greater than or equal to 4, since it turns a total of 4 times. And the last example that we have is that this polynomial behaves like the power function that decreases, and this occurs when our exponent is an odd number. So the degree of this thing will equal to some odd number that's going to be greater than or equal to 3. Sorry about that. Let me zoom in. That's going to be greater than or equal to 3. And the leading coefficient, this value of a, has to equal to a negative number in order for this end to be up and this end to be down. Again, in order for it to have the same end behaviors as this power function here. So that would be the answer. Your leading coefficient would have to be some negative number, and your degree would have to be an odd number that is greater than or equal to 3. Well, that concludes again our review. If you do have any questions, please send me a message on Remind or through email. Again, I appreciate you watching, and I hope you have a wonderful day. Goodbye.